Welcome to The Explainer. Today, we're tackling a really critical shift happening in AI, one that goes way beyond just asking good questions. We're moving from simply talking to AI to actually architecting the entire world they operate in. And this new discipline, it's called context engineering.
Okay, so let's just dive right in. For the last couple of years, all the buzz has been about prompt engineering, right? Which, let's be honest, is really the art of crafting that one perfect question. But the industry is making a pretty big pivot now to context engineering, and this is totally different. This is the science of building the entire information environment for an AI, which makes its answers way more reliable and predictable.
So what is it formally? Well, as you can see, context engineering is all about systematically managing an AI's working memory, what engineers call the context window. The whole goal here is to build systems that aren't just more accurate, but are also cheaper to run, by making sure every single piece of information we feed the AI is genuinely relevant. So you might be wondering, how do engineers actually structure all this information? It's not just a random data dump. It really comes down to two core frameworks that help organize the what and the how of the information the AI gets. First up is something called the context pyramid, and this is a really brilliant way to think about information based on how often it changes. You see, at the bottom, you've got the persistent layer. This is your foundational, stable data that rarely changes. In the middle, there's the dynamic layer for task-specific info. And right at the very top, you have the ephemeral layer for immediate, fast-changing data. Now, what's really fascinating about this slide is how it breaks it all down. That persistent layer, with things like system prompts and safety policies, is absolutely perfect for something called context caching to save on costs. The dynamic layer with search results needs constant re-ranking and summarizing, and that ephemeral layer with the user's latest query needs aggressive trimming to keep it focused. So you see, each layer gets its very own strategy. And while the pyramid is the what, the context supply chain is the how. It's a great analogy. It treats context like a product moving through a factory. It all starts with ingesting raw data from, say, PDFs or websites. Then it moves to a transformation stage, where an LLM actually enriches the data itself, creating summaries or pulling out key entities before it's even used. All right, so with those frameworks in mind, let's get into the real nitty-gritty engineering decisions. Because even with today's absolutely massive context windows, how you format and position information has a huge impact on both performance and cost. One of the most critical decisions is simply, what format do you use? While you've got options like JSON or XML, there is a growing consensus, as this quote points out, that one format is pretty much always the superior choice because of its simplicity and efficiency. And this just illustrates it perfectly. Markdown is the most token efficient, which really just means it costs less to use. But then look over at XML, it can be 80% more verbose, and all its repetitive tags create so much visual noise that it actually becomes the most error-prone format for an AI to understand. But it's not just about format. It's also about where you put the information. And this leads to a pretty surprising weakness in even the most advanced models out there. They have a terrible memory for things you bury in the middle of a long document. This chart shows the lost in the middle problem so clearly. You get this U-shaped performance curve. The model remembers stuff at the very beginning and the very end with almost perfect accuracy, but its recall can absolutely plummet to below 50% for anything you stick right in the middle. So what's the solution? Well, it's surprisingly simple, but it is absolutely crucial for reliability. Engineers now strategically place the most important facts at the beginning and the end of the context window. It's all about working with the model's inherent biases, not trying to fight against them. So when you combine all these different challenges, from choosing the right format to strategically positioning your documents, it becomes really clear why the industry is moving toward a future that is standardized, economically minded, and ultimately context first. And the economic incentive here is just massive. We mentioned context caching earlier. For those really complex, repetitive tasks where you're sending the same foundational info over and over again, features like this can cut your costs by up to 75%. That is a huge driver for adoption. Now, to solve what is basically an integration nightmare of connecting every AI model to every data source and tool, the industry is developing a new standard. It's called the Model Context Protocol, or MCP, and you should just think of it as a universal adapter, like a USB-C port for AI systems. So what MCP does is it creates a universal language between three core components. You have the host, which is the AI application you're using. You've got the server, which could be an external tool like a weather database, and then right in the middle, you have the client, which acts as this universal connector. This standard makes it dramatically simpler to build powerful modular AI systems. And all of this, it all points to a new core engineering principle: contextual density. The goal is no longer just about having the biggest context window. It's about packing the most useful, high-signal information into every single token you use. It's really about quality over quantity.
And this all leads us to a final, pretty thought-provoking question. Moving forward, is the real measure of an AI system its raw intelligence, or is it the intelligence of the world we build for it? The big takeaway here is that the future of AI isn't just about building bigger models, it's about building better worlds.